One of the surprising features of pressure in a fluid has to do with how the pressure is spread out over the fluid. So pressure is defined by being the force per unit area. What if we flip the script and apply a force to a liquid? Does the pressure increase? Yes. So for example, the heart increases blood pressure by pushing on blood. However, it works much better in an enclosed system. In an open system, if you push on the fluid, it will raise the level elsewhere, but with minimal change in the pressure. But if the system is enclosed, say pumping air into a closed bottle, then the pressure will increase. The striking thing about this increase in pressure is that it is transmitted to all parts of the fluid. Because the atoms in a fluid are free to move about, the pressure increase is evenly distributed over the entire fluid. This concept is called Pascal's principle and is stated more formally as a change in pressure applied to an enclosed fluid is transmitted undiminished to all portions of the fluid and the walls of the container. One important thing about Pascal's principle is that if we know the pressure at any one point, then we know the pressure for the entire fluid at that height. This also means that the pressure of a fluid is equal to the sum of the pressures. So as we just talked about when thinking about the pressure under a depth of water, you probably need to include both the pressure caused by the water and the pressure caused by the atmosphere and add them together. Probably the most important application of Pascal's principle is hydraulics. So let's consider an enclosed fluid that has two pistons attached to it. One piston has a very small area and one has a large area. In our example here, the small piston has a surface area 50 times smaller than the large piston. So let's say we push down on the small piston. We are applying a force over a small area, so the pressure will increase very rapidly. A moderate force divided by a small area will lead to a very large change in pressure. That pressure is then spread out over the entire fluid. That means that when we reach the large piston, the pressure has increased. Because the change in the pressure is the same change in pressure at the small piston is equal to the change in pressure at the large piston. However, the total force is equal to the pressure times the area. Because the area of the large piston is larger, the force applied by the large piston is 50 times larger than the force applied at the small piston. This means that the hydraulic system can be a force amplifier. A small force applied to a small piston equals a large force at the large piston. So to be more quantitative about it, the forces on piston 1 divided by the area of piston 1 is equal to the force on piston 2 divided by the area of piston 2. If we rearrange this question, then force 2 is equal to force 1 times the area of 2 divided by the area of 1. So the larger the area of 2, the larger the force on 2, and the smaller the area of 1, the larger the force on 2. Basically, you multiply the force by the ratio of the areas, with the piston with the larger area having a larger force. Make sure that your units for area are the same on both sides, although as long as you are consistent, you can use whatever units you want, say a centimeter squared on both sides or a meter squared on both sides. This may seem like a bit of a free lunch, so what's the catch? Well, you have to move the small piston much further than the large piston. The work done by the two pistons must be equal, so you need to push the small piston a larger distance to move the larger piston a small distance. Or I suppose you could push the large piston a short distance and then cause the small piston to move a large distance. The formula for this is A1 over A2 is equal to D2 over D1. So the larger the area, the smaller the distance, and vice versa. Next, I'll work through a quick problem. So we have a 1,200 kilogram car on a hydraulic lift. The small piston has an area of 65 centimeters squared, and the large piston has an area of 3,900 centimeters squared. I would like to know how much force do I need to lift the car? Well, I'll start by writing down my formulas for the force of a piston. I'll call force 1 the force I need to apply, and divide it by the area of 1, and that is equal to the force 2 divided by the area 2. If I plug in my numbers, I get force 1 divided by 65 square centimeters equal to the weight force, so 1,200 kilograms times the gravitational acceleration, 10 meters per second squared. Then I'll divide it by 3,900 centimeters squared, the area of the second piston. So I rearrange this to solve for force 1, and I get the weight divided by 3,900 centimeters squared times 65 centimeters squared, and that is equal to 200 newtons. Notice I'm multiplying the large force by the ratio of the small area over the large area to get the force needed on the small piston. 200 newtons corresponds to about 20 kilograms of weight, so a normal person can pretty easily provide that with a foot pump. That means that using hydraulics, a person can lift up a car. If you want to know the distance you need to push, then you would multiply the height you wanted to lift the car by the area of the large piston divided by the small piston. So that distance you will need to push is going to be much larger than the height that you want to lift the car. The ratio of the areas is 60, so you will want to, and so if you want to raise the car by 1 meters, then that means you would need to push the small piston in 60 meters, so you have to push it a large number of times. Okay, so it's your turn. I think you have a problem that's very similar to this one. Good luck.